All right, this is a lecture on what are called eigenvalues and eigenvectors. And the whole idea of an eigenvalue and eigenvector starts with a very simple question. If I was to consider a linear transformation that is going from Rn to Rn, and it's important to note there that I have n on both sides, so that the transformation that's induced by the matrix A, that matrix A will be n by n, which means that it is square. And what I'm wondering is it possible for me to have a transformation such that some vector x, when it's plugged into the transformation, is going to be equal to lambda times x, where this lambda is a scalar? And let me try to draw you a picture of what I'm talking about. For example, if I was looking at a transformation that was going from R2 to R2, then I can draw you a picture of that transformation. So it's possible that maybe the vector x looks like this, and then when I plug it into the transformation, I get out a new vector, t of x. Maybe it's longer, maybe it's shorter, maybe it points in the same direction, maybe it points in a different direction. Well, my question about having t of x be equal to lambda x is it possible that there's a different vector x such that when I plug the vector into the transformation, what comes out is pointing in the exact same direction as what went in? Scalar multiples of vectors point in the same direction and maybe don't have the same magnitude, maybe longer, maybe shorter. And so the magnitude with which this is longer, if it's twice as long, then that would imply that the value of lambda was equal to 2. So that's the question, which is a pretty straightforward question, but it leads to some pretty incredible results. So let's see if we can figure out what would need to be true in order for this to happen. So I know how to evaluate t of x because I have this matrix A, and so it would have to be the case that A times x is equal to lambda times x. These vectors x that satisfy this, and that is the exact same vector on both sides, this is what we will call an eigenvector. And the value of lambda will be called an eigenvalue. And this right here, ax equal to lambda x, is called the eigenvalue equation. Okay, great. Let's see if we can figure out some stuff about the eigenvalue equation. So if I was to just do some math, let's see, ax equal to lambda x, I could say that what would have to be the case is that a times x minus lambda x would have to be equal to the 0 vector. And then both of those have x's on the right side, so I could factor out an x on the right side, which would be a minus lambda. And since lambda is a scalar, that would be multiplied by the identity. And then x would be there, and then that would have to be equal to 0. And you should recognize that this is just a homogeneous system of equations. And we know lots of stuff about homogeneous systems of equations. We know that they're always consistent, that it has the trivial solution, which if we were to go back up here, you could immediately recognize that if I let x equal 0, clearly the left side is going to be equal to the right side, but it's not going to be very interesting. What I would really like is for this homogeneous system of equations to have non-trivial solutions. So the question becomes, what needs to be true about the coefficient matrix, which notice that the coefficient matrix is A minus lambda I. So what needs to be true about that in order to have non-trivial solutions? Question mark. Well, let's see. A is square, I is square, so this whole A minus lambda I is going to be a square matrix. And if I want this to be to have non-trivial solutions, then what I would need is all things on the invertible matrix theorem to be false. And there's a whole lot of things on the invertible matrix theorem. So I could say that A minus lambda I is not invertible. I could say that the columns of A minus lambda I are linearly dependent. We've got a whole lot of things that we could say would have to be true. The one that we will use is about the determinant because it works out really nice for the computations that we need. So if I need for the invertible matrix, the items on the invertible matrix theorem to be false, then that is going to imply that I need the determinant of A minus lambda I to be equal to 0. That will make everything on the invertible matrix theorem false, which will mean that it has that the homogeneous system has non-trivial solutions. Let's say that I had a matrix A which was 1, 3, 2, 2. And I wanted to evaluate this determinant of A minus lambda I. So I know that I need to calculate the determinant of A minus lambda I. So I'll start by looking at the determinant of 1, 3, 2, 2 minus lambda times I, which would be the identity matrix multiplied by lambda, so it would have lambdas going down the main diagonal. And I would do that inside there first, so that would be 1 minus lambda, 3, 2, and 2 minus lambda. And that is something that's easy to calculate. I multiply down the main diagonal, so I would have 1 minus lambda and 2 minus lambda minus what I get multiplying the off diagonal, which is 6. And then multiply that out, so that would give me 2 minus 3 lambda plus lambda squared minus 6. And I could write that as a polynomial, which is lambda squared minus 3 lambda minus 4. So this is the determinant of A minus lambda I. We will also call this the characteristic polynomial. The characteristic polynomial. That is just a definition, and it is something that we will use frequently throughout this chapter. Now, the eigenvalues are the roots of the characteristic polynomial. So what I really care about is, when is lambda squared minus 3 lambda minus 4 equal to 0? And in this example, it conveniently factors, so that would be lambda minus 4 and lambda plus 1 is equal to 0. And I get that lambda could be equal to 4, or it could be equal to negative 1. So that tells me that this matrix has got eigenvalues of 4 and negative 1. So when I go back to thinking about my eigenvalue equation, which is AX is equal to lambda X, what I have found is that there will be solutions when I let lambda equal 4 and when I let lambda equal negative 1.